We tend to think of data points as independent events, but in a time series, the present is almost always tethered to the past. What happened yesterday casts a shadow on today. Some datasets have zero memory. A scatter plot of white noise is completely random. But look at daily temperatures or an ECG heartbeat. These systems have strong, predictable memory. Today's high temperature is closely related to yesterday's. To build an accurate forecasting model like ARIMA, we can't just guess at these patterns. We have to mathematically measure the exact shape and duration of that memory. We do this using two specific statistical tools, the autocorrelation function, or ACF, and the partial autocorrelation function, or PACF. Mastering how to read these two plots is what allows us to move from blindly guessing at future trends to calculating exactly how historical data dictates future values. Autocorrelation is a measurement of how strongly a current dataset aligns with a delayed, older version of itself. We start with a window called lag 1. This is where we compare today's value directly to yesterday's value. To see this, we take our primary data wave and compare it against a secondary version of that same wave, shifted back by exactly one data point. When these two waves line up closely, we get a high correlation score. Now watch what happens if we widen that comparative window to a lag 24, comparing today's value to the value from 24 days ago. The alignment breaks down, and our correlation score drops significantly. This drop is known as memory decay. Generally, the older the data gets, the less influence it exerts on the present moment. Instead of calculating these shifts one by one, we visualize all correlation scores simultaneously across multiple lags using a bar chart called a correlogram. By looking at the ACF correlogram to see where the correlation slowly decays or cuts off sharply, we can determine the exact moving average, or MA, order required for an ARIMA forecast. The ACF gives us a complete picture of the total historical echo. However, it calculates the total correlation, which means it cannot distinguish between original signals and mere chain reactions. That is the trap of indirect influence. Consider a simple linear sequence. Day 1 directly impacts day 2, and day 2 directly impacts day 3. Because day 1 affects day 2, it indirectly affects day 3. In a standard ACF calculation, this mathematical overlap creates an illusion, making it look like day 1 directly controls day 3, even though day 2 is the actual catalyst. The partial autocorrelation function solves this. The PACF acts as a mathematical filter. It strips away the intermediate steps, in this case the effects of day 2, and isolates only the true direct influence of day 1 on day 3. By finding this specific lag where the PACF plot cuts off sharply, we determine the exact autoregressive, or AR, order for our forecasting model. If the ACF shows the entire tangled web of history, the PACF cuts out everything except the direct structural pillars of the data's memory. We don't have to calculate these complex mathematical filters by hand. We can execute them directly in Python. For time series graphics, the statsmodels library provides the standard toolkit. We simply import the ACF and PACF plotting functions. Next, we feed our raw time series dataset into both of these functions. It's important to define the lags parameter, for instance, setting lags equals 40. This caps how far back the algorithm searches, keeping the computational load manageable. Run the commands, and Python renders our visual charts. Generating these two correlograms is the necessary first step before configuring your ARIMA forecasting script. These are the generated ACF and PACF plots. Notice the horizontal band across the center. This shaded blue zone is the statistical significance threshold. Any vertical bar trapped inside this zone is mathematically meaningless white noise. But look at the spikes protruding outside the boundary. Here, we see large spikes at exactly lag 4 and lag 8. This repeating pattern is concrete proof of a seasonal memory cycle within the dataset, in this case, a strong quarterly rhythm. By isolating these exact points of significance, you identify the correct AR and MA parameters for your ARIMA model and confidently turn historical echoes into